Thank you. But a single subatomic elementary particle in the primordial gas, when the universe was the size of a baseball, carried enough energy to, in a single collision, knock the same dust speck not only right out of the water, but out of the earth. Goodness, very extreme conditions back then, very. If we tried to ratchet up such a collision to a human scale, it would be like accelerating a rocket in space to such a high speed that upon colliding with the moon, it could kick it right out of the solar system. Of course, the moon would first actually break apart, um, as with a dust speck in the subatomic analog, but that is not the point. Gulliver never witnessed phenomena as foreign as this in all his travels. So this is quite foreign to us. How the universe was in the beginning is, of course, very foreign to us. We've come a very long way in the evolution of the universe to the point where we exist now. That is a very different universe than what it used to be when it first got started. Okay. So that's why it's difficult for us to not only imagine these things, but also to achieve these things technologically if we're trying to recreate some sort of conditions from the beginning part of the universe to kind of probe these physics of the subatomic particles. Not only did such incredibly energetic collisions occur in the early universe, they occurred often and everywhere. Remember that in a region the size of a single present-day atomic nucleus, there were then more than enough particles to comprise 1 billion nuclei. Moreover, the collision rate was so high that in 1 second, each particle in the early proto-universe would have been able to engage in more collisions than there are grains of sand on Earth. Do you see where this is quite different? But of course, 1 second is an eternity compared to the actual age of the universe at that time. Indeed, 1 second is far more than 1 trillion times longer when compared to the age of the universe at that time than the age of the universe is today when compared to 1 second. So the age of the universe is a lot bigger today, but when the universe is getting started, 1 second is a long time, right? So these are the conditions when the gist of our oxygen atom came to be, when nothing became something. How can I say nothing when there, in fact, was orders of magnitude more energy in a volume the size of a head of a pin at that time than is contained in our entire observable universe today? The point is there was a lot of stuff, but not the right stuff. In spite of the mismatch between the mini world created momentarily during the collisions at CERN and the phenomenal collisions in the very early universe, they have one thing in common. In both, energy is directly converted into mass and vice versa. So we know about mass energy equivalence from special relativity, from special theory of relativity by Einstein. So of course this is possible. A striking example of the verity of Einstein's theory of relativity. When the universe was the size of a baseball, the energies involved in the collisions of pairs of particles were so great that 1 billion newly created particles could in principle spew out of the collision of just two colliding energetic electrons. And collisions were occurring so fast that no single particle preserved its identity for long. Electrons smashed together to make quarks, and quarks smashed together to make particles of radiation, photons, and all of these smashed together to make unknown particles that may last have existed in nature when the universe was less than a billionth of a second old. How can we make sense of such a mishmash? Thank you, Bing Top Marot. Thank you. This is precisely the problem faced by elementary particle physicists as they attempt to explore the fundamental laws of physics at accelerators. So the universe was really young, less than a second old, when this is what we're trying to probe in these colliders. And that's very difficult. Getting the conditions to be similar to that universe is very difficult. When we bang together two beams of particles in the LEP collider or in its higher energy cousin